Okay, thank you. Hello, everyone. I'm honored to speak here today. I'm Cheng from Tsinghua University, and I will present the paper titled High Frequency Audio Devices Based in Audio Ultrasonic Hand Tracking System Using Subspace Method. So this presentation includes 5 parts. Let's start with the introduction. Hand tracking, a crucial form of human-computer interaction suitable for mobile devices and personal computers, allows continuous interactive operations such as volume control and brightness adjustment. Figure 1 demonstrates a system design concept for gesture recognition and interaction based on sound waves using the built-in microphone and speakers of a smartphone. Figure 2 showcases Google's approach, using millimeter wave radar chips for gesture sensing and interaction. So we focus on the acoustic and ultrasonic-based approaches because those offers advantages of high privacy, protection, and low power consumption. While solutions based on audio codec and microphone speakers have gained attention because of their convenient deployment feature. So, however, audio codec-based systems face several challenges. Due to the limitation of devices' working bandwidth, and the modulation is often required to enhance system performance. However, issues such as speaker response and the spectral leakage can make the sound wave audible and unsuitable for continuous operations in the presence of people. Phase accumulation and FFT-based ranging methods face error accumulation and cannot achieve high distance resolution. So the distance information folding when the distance of the hand is further than the unambiguous range, and in the near-field hand tracking scenario, as shown in Figure 4, multiple scattering centers exist in the hand. But since we're more concerned is the virtual center, which could briefly represent the movement of the hand. So as shown in Figure 5, if the hand moving with a fixed posture, an algorithm which could calculate the virtual point stably is important for the tracking. So we propose a solution to address those challenges. Distance estimation through phase difference between different frequency points using multi-frequency continuous wave to ensure inaudible sound, and utilizing the subspace method for feature selection and range time map generation to deal with the multi-scattering center and error accumulation issues. And we are addressing the distance folding with the help of a particle filter. So this is the setup of our system. Our system is depicted like this, with two speakers on the PCB board and a microphone on it. The speakers emitting multi-frequency continuous wave at different frequency points, and a microphone receiving echoes. A 6-bit 96 kHz sampling rate audio codec is used for the synchronized signal transmission and receiving. And this is the data flow of our system, processing flow of our system. The digital domain IQ demodulation, static cluster separation using circular fitting, and the range-time map generation based on the subs method we mentioned before, and the tracking with the particle filter were all finished on the PC. So let's focus on the algorithm design. Multi-frequency continuous wave have many similarities to the uniform linear array, and the near-field target reception of the multi-frequency continuous wave is quite similar to the far field of the uniform linear array, and it can be viewed as a Euler system constructed in the frequency domain, as the delta F is the frequency step. So it can be viewed as a where the same target has the same time delay, but different carrier frequencies result in phase difference between the frequency points. So here we display the waveform transmitted of the system and the baseband signal of one channel. This is the right channel, and this channel's baseband signal after modulation looks like this. And what we considered is the distance of the target, and it can be encoded in the phase part. So similar to the uniform linear array processing, we can derive the steering vector of right channel at a specific distance. Once we create this equation, so the right channel baseband signal can be expressed in the matrix form. So with a fixed time length, we can formulate the received module and use autocorrelation to divide the signal into two spaces, which are signal space and noise space, subspace. So as shown in figure 9, the blue matrix, this one, represents the autocorrelation matrix of the measurement matrix, and it can be decomposed into three matrices on the right-hand side of the equation. So the yellow one represents the matrix, represents the feature vectors of the system of the blue matrix, and the blue and the green one is the eigenvalues. So the green one is a diagonal matrix. Once we using the singular value decomposition method to got those two matrices, and we can try to use it to generate the distribution of the distance by calculating the reciprocal of the inner products of noise subspace feature vectors and the steering vectors within all unambiguous distance. So the rational division of the signal and the noise subspace is important. So we properly participating in the subspace is crucial for denoising and feature extraction. Due to the correlation between multi-scattering centers on the hand, spatial smoothing and decorrelation are required in the frequency domain. So after decorrelation, the matrix rank need to be set as 1 to find the most significant reflection components. So the particle filter is used to estimate motion states through Monte-Carlo method. The figure 9 shows distance folding in the RTM generated by the subspace method. Using the known sudden changes property during particle filter prediction and resampling, we can unfold distance jumps into the original motion trend. So key to this is the calculation of the particle weights. We calculate weights by correlating the predicted distance between vectors with the measured distance between vectors. And the weighted average of distance response by all particles is the measured distance value. So here move to the experiment part. The experiment setup is shown in figure 11, and we use a high frame rate camera to synchronize the radial motion trajectory and captured by our proposed system and calculate the span error, which is this equation. In the example, if the data is divided into two frames with the yellow and green color, and the distance results of each time is represented as a blue square, the calculation procedure of the span error is shown like this, where the estimated distance and the real distance are all concerned. Compared to obtain distance using arctangent with unwrapping or DACM, which is a method using phase information and don't need the unwrapping procedure. Our method has smaller span error, and figure 12 and 13 illustrate the difference between our method's runtime map and the runtime map created by the Fourier inverse transform method. Our method provides better feature selection and noise separation performance. And the figure 14 displays one-dimensional tracking results, showing that our method can better depict the radial hand motion in the span domain. So in contrast, the phase unwrapping and averaging method has a trajectory errors at the frequency 2. So leading to a performance drop as seen in the figure 15. And figure 16 demonstrates the two-dimensional motion tracking results using our system no transmit single received feature. And in summary, our work can be summarized like a hand tracking system that utilizing audio devices and hardware is proposed. And the Subspace method is used to address the challenge of tracking multiple scanning center targets. The using of practical fields helps to solve the challenges of distance folding, and our system exhibits better one-dimensional tracking performance in human-computer interaction scenarios. So, thanks for your attention.